Greetings, welcome back to the channel. In our last video, Engine Fundamentals 2, we looked at how combustion takes place in a piston engine and how combustion takes place in a gas turbine engine. We looked at the difference. If you haven't watched this video, you will find the link to this video in the description below. In this video today, we are going to be looking at the construction of a gas turbine engine. We'll particularly focus on the engine intake and the compressor. In our next video, we'll look at the combustion chamber, the turbine, and the exhaust section of a gas turbine engine. So welcome and enjoy the video. A gas turbine engine is made up of 5 modules. These modules, or also called parts of the engine, are as follows. There is the intake. Second, there is the compressor. Thirdly, there is the combustion chamber. Fourth part is the turbine section of the engine. And lastly, there's the exhaust section of the engine. In this video, we'll focus on the intake and the compressor of a gas turbine engine. The intake is most of the time considered as part of the airframe of the aircraft. But in this video, we'll look at it as a part of the engine because the engine cannot function without the intake. It is the engine intake that provides the air that is needed for the operation of the engine. So the engine cannot function or cannot operate as it should without the intake. The function of the gas turbine engine intake is to deliver air in the correct quantity and pressure to the compressor as is required by the engine. There are 2 requirements for a gas turbine engine intake that is related to the engine and 1 requirement that is related to the airframe in general. The gas turbine engine intake has to recover as much of the total air pressure from the free air stream and deliver this air in the right quantity to the compressor with minimum pressure variation. Second requirement of the gas turbine engine is it has to deliver the correct amount and quantity of air at all operating conditions of the engine. So this is the second requirement of the gas turbine engine regarding the engine. Now, there's 1 requirement of the gas turbine engine intake that regards the airframe in general. And this requirement is that a gas turbine engine intake has to keep to a minimum the air resistance or the drag that it creates. It has to be properly streamlined and everything so that the drag that will be created by the intake is kept to a minimum. There are 2 types of gas turbine engine intakes. 1, intakes that are used for supersonic aircrafts, and 2, there are those intakes that are designed to be used on aircraft that flies subsonic or for subsonic aircraft. Subsonic aircrafts are those aircrafts that flies at speeds below the speed of sound. Supersonic aircrafts are those aircrafts that flies at speeds above the speed of sound. For subsonic aircraft, the intake shape is a divergent shape. If you can remember the Venturi effect, as the air flows into the intake, when it reaches the divergent portion of the intake, the velocity of the air is decreased and the pressure of the air is increased subsequently. And this is what is needed because as we go through the compressor, we need the pressure of the air that is coming into the engine to increase gradually before it reaches the combustion stage. So when the air passes through the divergent shape, which is the shape of a subsonic air intake, the velocity of the air is reduced at that divergent portion and the pressure is subsequently increased as the air travels through the intake. This is the first type of air intake found on a gas turbine engine, which is used on subsonic aircrafts. Now, on a supersonic aircraft, there is what is called a convergent divergent intake. It's called a CD duct. And this convergent divergent intake, what it does is that As the supersonic airflow flows into the intake, it reaches the point where there is a restriction, the convergent portion. As it reaches there, the velocity of the air is reduced. As the velocity is reduced, the pressure of the air is increased. I want you to note something. For supersonic flow, as per the Venturi effect, when the air reaches a restriction, for a supersonic flow, the velocity of the air decreases. But for a subsonic airflow, as the airflow reaches a restriction, the velocity increases. That is the difference. For a supersonic flow, when the airflow reaches a restriction, the velocity of the airflow reduces, increasing pressure. While for subsonic airflow, if there is a restriction and the subsonic airflow is allowed to flow, when it reaches the restriction, the velocity will increase and the pressure decreased. So that is the difference that I wanted to point out in order for us to understand how the air flows in a supersonic aircraft engine intake. So as the airflow in the convergent duct, when it reaches the restriction or the restricted portion of the intake, the velocity of the supersonic airflow is reduced, and as the velocity is reduced, the pressure of the air is increased. This reduction in velocity is needed because for an engine to work, it needs air that is flowing below the speed of sound. The engine cannot support or cannot do its function properly with airflow that is above the speed of sound. So the speed of the airflow has to be reduced to subsonic for it to be accepted by the engine in order for the engine to work as it should. So as the supersonic airflow reaches the restriction, the speed is reduced and the pressure is increased. During this process, a shockwave, a normal shockwave is created just at the restriction, of the restricted portion of the convergent divergent duct. A normal shockwave is created there. Now, as this now subsonic airflow passes through the normal shockwave, the velocity of the airflow is further decreased to lower subsonic velocity, which is what is needed for the engine operation. So for supersonic airflow, a convergent divergent duct is used. For subsonic airflow, just a divergent intake is used for engine operation. For a convergent divergent duct, there is a wedge that changes the shape of the intake according to the condition or according to the airspeed of the aircraft. If the speed is subsonic, the wedge will retract, and thus the intake will remain as a divergent subsonic intake. But if the airflow is supersonic, the wedge will extend, causing a restriction in the intake. This is what that forms the convergent divergent duct or shape of the intake of a supersonic engine intake. Those are the two types of a gas turbine engine intake. Now there's a function that is incorporated in a gas turbine engine intake to prevent disturbance of the air that goes through the engine, especially during snowy weather and during cold. This is an ice protection system. This prevents the formation of the ice at the lip of the intake, because this formation of the ice at the lip of the intake will cause disturbance in the airflow that flows to the engine, and this can lead to pressure variations and a lot of things that we don't want to happen to the engine. So to prevent this, there's ice protection that is incorporated on the engine, and this is achieved through two methods. One, there is hot air that is allowed to flow just underneath the surface of the air intake, and this hits the intake and prevents formation of the ice at the engine intake. Secondly, there is an electrical method whereby the engine intake is heated, and as the engine intake is heated, the ice formation is avoided or is prevented because of the increased temperature of the air intake. Next, we are going to be looking at the compressor section of a gas turbine engine. The compressor is the section that is found between the intake and the combustion chamber of a gas turbine engine. The function of the compressor is to compress the air that it gets from the intake to the right pressure and quantity and deliver this air to the combustion chamber for combustion. There are two types of compressors that are found or that are used on a gas turbine engine. One is a centrifugal flow type compressor, and secondly, there is an axial flow compressor. A centrifugal flow compressor is made up of an impeller, which is a rotor, and a diffuser, which is a stator, and there is also a third part, which is called a manifold. For an axial flow compressor, there is one, a rotor, two, there is a stator, and these two, the rotor and the stator, are the major components on an axial flow compressor, and they form what is called a compressor stage. One rotor and one stator compose what is called an axial flow compressor stage. For a centrifugal flow compressor, one impeller and one diffuser makes a stage of a centrifugal type compressor. So let's look at how these two compressors function. One, the centrifugal type compressor allows the air to flow into the center of the impeller, that is the eye of the impeller. As the air flows into the eye of the impeller, it is accelerated outwardly as the impeller rotates. And as it is accelerated outwardly, the velocity of the air is increased. And from the impeller, this air that has an increased velocity flows to the diffuser. The shape between the impeller and the diffuser is a divergent shape. As the air flows from the impeller to the diffuser, the velocity that was increased by the impeller is reduced, thus increasing pressure of the air as it flows through the diffuser. From the diffuser, this air passes through the manifold that directs the airflow either to the combustion chamber or to the next stage of the compressor. So that is the function of those components that we mentioned that forms a centrifugal flow compressor. As one stage of a centrifugal flow compressor can cause a pressure increase to about a pressure ratio of 8:1 for one stage of a centrifugal flow compressor. But a lot of centrifugal compressors use about 2 stages of the compressor, because as the number of stages of a centrifugal flow compressor increases, the efficiency of the compressor is decreased. So most of the centrifugal flow compressors are limited to only 2 stages with a pressure ratio increase of about 8:1 per stage. For an axial flow compressor, pressure rise per stage is minimal compared to that of a centrifugal flow compressor. For an axial flow compressor stage, there is a pressure increase of about 1.2 to 1 per stage. But on an axial flow compressor, compressor stages can be as much as 16 stages per compressor. To cater for the minimum pressure rise per stage, the number of stages of an axial flow compressor are much more than that of a centrifugal flow compressor. In an axial flow compressor, the air flows from the first stage of the compressor to the rotor. The air continues to flow in the axial direction. The direction of the air is not changed. That's reducing the pressure variations caused by turns inside the compressor. So in an axial flow compressor, unlike the centrifugal flow, where air is accelerated outwardly in a centrifugal direction, in an axial flow, the air flows in the axial direction from the intake going to the combustion chamber. So those are the two differences between a centrifugal flow compressor and an axial flow compressor. Now, there are veins in between the stages of the axial flow compressor, and these veins guides or controls the direction of the airflow inside the compressor. The veins that are found before the first stage of the compressor, they are called the inlet guide veins. And the veins that are found at the last stage of the compressor just before the air is sent to the combustion are called the outlet guide vanes. These vanes controls the direction of the air, and these vanes can be fixed or they can be variable. They can change their angle, and for those that changes their angle are called variable guide vanes. As the air travels inside an axial flow compressor, the velocity of the air remains unchanged throughout the compressor. To achieve this constant velocity inside the axial flow compressor with a variation in the pressure inside, the diameter of the passage of the air inside the axial flow compressor gradually decreases from the front of the compressor to the rear stage of the compressor. This is achieved in two ways. One, there is a gradual decrease in the diameter of the compressor. That is one way to reduce the passage in order to keep the velocity constant in an axial flow compressor. The second way is through the increase in the compressor disc, in the disc of the rotor, gradually as the compressor stages move from the front to the back. And this gradual increase in the compressor disc reduces the size or the passage in which air flows in the axial compressor from the front to the back, thereby keeping the velocity as constant as possible while increasing the pressure as you go through the stages of the compressor. So the compressor has two functions, or the airflow of the compressor is used for two functions. One, combustion function or combustion purposes by the engine, and two, bleed air for other systems that we discussed in our video concerning the pneumatics of an aircraft. If you haven't subscribed to the channel, we kindly request you to subscribe to the channel, and we also remind you to turn on your notifications so that you'll be notified each and every time we post a new video. We value you and thank you for watching the video till the end. I'll see you in our next video. Bye-bye.